Anyway, we'll go ahead. So hope it is visible.
Yes, sir.
So I have started recording. So if you recall what we have studied in last class, we have discussed something about the direct shear test, okay, where we will apply different normal loads and shear loads where soil shears. We'll note it down the reading, dial gauge reading, and we can plot the graph. From the graph, we can get the C parameter intercept and the angle of internal friction phi. Okay. So likewise, those C5 parameters are very important for designing a structure or a foundation. We will see in the next semester. Okay, the C and the phi parameters are very important. Okay, because based on that only we can classify the soil like different types of soil. Okay, cohesionless soil will have more angle of internal friction, that is phi value. Okay, and cohesion would be zero in cohesionless soil. Okay, cohesion would be zero, C would be zero. Okay, and in the case of purely cohesive soil, that means there is no sand particles. Okay, whole clay soil only will have only cohesion, C term, no phi term. Phi would be zero. Okay, in the cohesionless soil, C would be zero. In the cohesive soil, phi would be zero. But there are soils we have which have both. That is called, we call it as CEPC cell, general cell, whatever you could see. Okay, that this type of soil will have C parameter and the phi parameter. Most of the soil you can say. Okay, so it's not that whole soil is cohesiveness, cohesionless or cohesive soil. So these are the different types of the soil. Okay, cohesive soil and the cohesionless soil, and the C5 soil, cohesive and friction soil. Okay, so now triaxial can be conducted for any soil. So now forget about our direct shear test, now focus on this our triaxial test. Okay, this is one of the most important and reliable test. Okay, so here what we have in the previous classes, we have three principal stresses: sigma 1, sigma 2, sigma 3. Okay, a major and intermediate and minor, and we have shear stress. Okay, in a particular plane. So what we do is we create this condition in the laboratory actually. So the soil, will take a soil sample. Okay, and it is fully subjected to confining pressure. Confining in the sense like under the ground, if you take a small particle, it would be confined with the all around pressure. So similar things we will try to simulate here. So we'll take a small sample. Okay, cylindrical sample. Anyway, I will show some pictures so that you will understand. Then all around that we'll confining by using the water, and the water pressure will confine it, and finally we'll apply a deviator stress and the I mean axial stress. Okay, which you will try to shear the soil. So that here, because the soil in cylindrical form. Okay, so sigma one would be the topmost axial load we will apply it. Okay, and the sigma 3 would be all around. Okay, so likewise here, so this soil sample would be subjected to sigma c, and here we'll apply, because top also sigma 3 everywhere. Okay, then we'll apply additional load, this is called the deviator stress, and sigma c plus sigma d deviator stress will equal to sigma 1, that's a measure principal stress, and this is a measure principal plane. Okay, and we minor principal stress. Understand? What we do is we'll create a simulation in the laboratory by using the water. Okay, pressure, and all around the sample the soil would be compressed. Okay, and we will apply deviator stress. Okay, that is sigma c plus extra d sigma d deviator. Then the sigma c plus sigma d whole thing is called the sigma 1. That's the measure, that's the maximum pressure it goes, right? That is called the measure principal stress, and minor principal stress would be sigma c, or we call it as sigma 3. Here sigma 2 and sigma 3 are equal. Okay, because of axial, so I mean cylindrical sample. Now this sigma 1 and sigma 3 will apply it, okay. And what general we do, we can measure the pore pressure, we can measure the there are two stages already I have told you, okay. One is the consolidated stage, second is the shearing stage, consolidation. Based on that also we have classified this file UU, CU and CD, unconfined, undrained test, confined, undrained, consolidated, undrained test, okay, consolidated, drained test. So quick test, then the medium test and the slow test. So likewise, these are all based on the pore pressure measurement and so many things we can do by using the triaxial test. We can measure the pore pressure, what it is developing in the soil, okay, and we can check the failure rate, and uh, we can allow the water to dissipate. Sometimes we can allow water to stop. So we can play with it, okay. So likewise, we can conduct this triaxial test, and we can again, what is the aim? Again, we can draw the Mohr circle. That's our ultimate aim, right? Are failure envelope and so on. Because we know sigma 1, we know sigma 3, we can draw the more coulombs, more envelope, okay. Because once we know sigma 1, sigma 3, and the deviator stress, that is the shear stress. Once we know that different loads at different sigma 1, sigma 2, sigma 3, and different load deviator stresses, we can plot a Mohr circle. Okay, x-axis would be normal and y-axis would be shear. When you plot a Mohr circle, keep on plotting it, draw a tangent to it, and it will give the failure envelope. Once you do failure envelope, again what it gives, C value where the y-axis it intercept, C again the phi angle of internal friction also it will give. So this C5 parameters, why we are measuring it? Because for a design, this cohesion and the angle of internal friction plays a major role, okay, while designing it. So likewise we can find out this uh, stresses, okay. What is Mohr circle? It is a graphical representation of this principal stresses and the principal strains are planes, you call it as a graphical representation we are doing, okay. So by using Mohr circle, so likewise we can plot the Mohr circle by using the direct shear test or by using the triaxial test shear test also, okay. So this is how the this is whole thing is given about it, okay. So triaxial test you can read once, okay, how the there are mercury which it controls the things, okay, how the water pressure would be measured with some diagram it is given, okay. So by using this one consolidated undrained test we can calculate, we can do it consolidated undrained test, okay, and consolidated drain test, okay, on the coefficient side and the coefficient less it is given, okay. Now coming to the merits and the demerits of the test, okay. There is complete control over the drainage condition here. What are the merits actually? In the direct shear test, because it was open, we cannot control it actually. So there is a complete control over drainage, and test can be easily conducted for all three types of sample. Okay, I mean drainage condition UU, CU, CD, and so on. Okay, pore pressure changes and the volumetric changes can be measured directly. The stress distribution and the failure plane also uniform, and the specimen is free to fail the weakest plane. You remember in the direct shear test, we ourselves define the failure plane there. Horizontal, we said that by this plane only soil will fail, and that's the reason we have moved the boxes. Okay, that's the shear box we call it as. But here what we'll do, all along the pressure will apply, we apply deviated stress, we allow the soil to fail, and we can observe it, how in which plane it is failing. Okay. Uh, More circle can be drawn, okay, then the test is suitable for accurate research work. So that is the reason all our PhD school students or MTech students, they do all these tests, triaxial test. It is more reliable and can be used for even our NIT also. We have this triaxial test, okay, and even we have cyclic triaxial also. Cyclic triaxial we can apply dynamic loads also, not only static. Cyclic loading 1, 2, 3, 4, 5 with cycles we can apply it, okay. So we have cyclic triaxial test also. So this test the apparatus will cost 30, 40, 50,000, right? Very costly. As the name's demerits are, operator is elaborate, costly, little bulky, okay, drainage take for a long period, okay, slowly, sometimes slow test, no, compared to the direct shear test, it takes a lot of time, okay. Sometimes the strain condition, this specimen may not be uniform and so on, okay. Uh, Then the test simulates only axisymmetrical problem, but in the field problem is generally three-dimensional again. Okay, so small demerits are there and some merits are also there by using this uh, test. Okay, so what we'll do is we can find so many parameters are given anyway. Before that, what we'll do is we can see some videos so that you'll understand what exactly this is. It visible?
Yes,
Please
sir.
respond. Visible?
Yes,
Yes,
sir, it is, sir.
Audible?
Starts by preparing the split mold.
yes, sir.
Yes, sir.
In some cases, it can
So
be
this what?
useful to apply.
Okay. So this anyway you will do in the laboratory when you come to NIT. And if you want to be
Starts by
MS
preparing
in
your
US,
specimen in accordance
abroad
with
and
your
you
test
have to do
standard.
these tests. Okay. So learn it.
Start by preparing your specimen in accordance with your test standard. Once you have trimmed your sample to size, you will need to remove the split mold. In some cases, it can be useful to apply a small amount of non-corrosive silicone grease along the groove of the two halves of the split mold to help reduce resistance. We recommend the use of PTFE silicone grease. If the specimen is stuck, use a disc the same size diameter as your specimen to apply evenly when pushing. Be careful not to damage the specimen in the process. Now you have removed the specimen, you can place it on the base pedestal of the triaxial cell. If you are running an effective stress test, it is important you ensure the triaxial base has been completely de-aired. If you have not de-aired your triaxial cell, please see the link highlighted in the video. The link is also available in the description below. Assuming the base has been de-aired, slide a saturated porous disc onto the base pedestal. It helps to have a pool of water on the base to keep the stone saturated and avoid trapping any air as you slide the disc on. If you are not measuring pore water pressure or applying, you may use plastic discs instead of porous discs. Now you have your triaxial cell ready, you can prepare your membrane. To place a membrane over a specimen, you will need to use a membrane stretcher. Start by checking your membrane for any holes by stretching it over some light. If okay, place the membrane in the center of the stretcher and fold either end over. The suction ball will act as a vacuum, sucking in the air between the membrane and stretcher, making it easier to slide over your specimen. Position the specimen on the base pedestal.
So that is the specimen. Okay, soil specimen UCC sample.
The membrane stretcher over the specimen without damaging it by using the suction ball. Once in position, remove the suction ball to release the vacuum. Roll both ends of the membrane off the stretcher. You will now need to secure the membrane in position with an O-ring using an O-ring stretcher. Slide the stretcher over the specimen and roll the O-ring down. Ensure the O-ring rolls onto the base pedestal and not onto the specimen. In some cases, you may wish to add a secondary O-ring to ensure the membrane is completely sealed. Another O-ring is required to secure the top of the membrane. Stretch another O-ring over the stretcher and place it on the specimen. You will need to do this before you put on the top cap. Place a saturated porous disc on the specimen and the top cap on top. Twist the top cap to avoid the drainage lead getting trapped when positioning the top half of the triaxial cell. Roll the membrane up over the top cap. Slide the O-ring off onto the top cap, being careful not to slide it onto the specimen. Remove the stretcher and fold the excess membrane down over the O-ring. You have now assembled your specimen for testing. Place the top of the triaxial cell onto the base and seal by screwing the locking nuts evenly. You may wish to apply a small amount of silicone grease on the O-ring to help avoid leakage. Position the cell in the triaxial frame. Open a path from the de-aired water tank into the triaxial cell. Ensure the bleed valve is open and fill the cell with de-aired water.
It's filling the water, okay? So that's the membrane we generally use because directly we cannot.
Once it is nearly full, be ready to close the valve as water begins to flow out.
So that is a sample preparation technique, okay?
Now your cell is ready.
So water added.
Adjust the ram and displacement sensor, ensuring you have enough travel length on the transducer to conduct your test. Complete a quick check, ensuring the correct valves are open and closed.
Yeah, vertical load.
If you are happy, you can begin your test. You may now configure a completely automated test using CLISP Studio software.
Hope you understood a little bit, and one more video also I will see.
Specimen during testing. Hello, this is Professor Kitch, and welcome to this webcast on section 12.9. This is the second of two webcasts covering a shear strength test. This presentation is a test. When you finish this presentation, you should be able to describe the boundary conditions for the uncombined compression test, sketch the setup for a triaxial test and show the applied loads and stresses, as well as draw a free body diagram of a soil specimen during testing. And finally, given data from a triaxial test, you should be able to plot the appropriate Mohr circles and determine the strength parameters phi and c. This is a picture of a typical triaxial test. The specimen being tested is located in the triaxial cell and enclosed in a flexible membrane. The triaxial cell is placed in a load frame. The purpose of the load frame is to apply a vertical load to the specimen. This load is measured by a load cell located near the top of the load frame. Tubing connects the cell to pressure and volume control modules, which are used to regulate and measure the pressure within the cell, as well as control the drainage of pore fluid out of the specimen. A computer data acquisition system controls the test and records the data. Now let's take a closer look at the triaxial cell itself. This figure illustrates the triaxial cell and explains how it applies stresses to the soil and how it controls drainage conditions. The specimen sits on a pedestal inside the cell with a loading cap on top. It is surrounded by an impermeable latex membrane that separates the soil and its pore fluid from the fluid that fills the cell. There are two pressure gauges attached to the cell. One measures the pressure of the fluid within the cell, and one measures the pore pressure within the specimen itself. There is a valve which controls drainage within the specimen. The valve can either be closed, thereby preventing drainage, or open, which allows for drainage. A loading piston on top of the cell allows an axial force to be applied to the soil specimen. A dial gauge attached to the top of this specimen lets us measure the vertical deformation. There are two distinct phases in any triaxial test. The first phase is the consolidation phase, during which cell pressure is increased. This provides a uniform confining stress all around the specimen equal to the minor principal stress, sigma 3. During this phase, the soil may be allowed to consolidate or not, depending on the type of test being performed. The second phase of the test is the shear phase. During this phase, a load is applied to the piston at the top of the cell. This load increases the stress at the top of the specimen. Since there are no shear stresses on either the top or the sides of the specimen, these are principal planes. The major principal stress, sigma 1, is applied to the top of the specimen, and the cell pressure provides the minor principal stress, sigma 3, to the sides of the specimen. The vertical stress is gradually increased until the specimen fails. This is a relatively simple schematic of a triaxial cell. Actual cells are more complicated and have additional drainage lines. However, this schematic covers the essential components of a triaxial cell. In actual lab testing, there is a phase that precedes the consolidation phase. This preceding phase is the saturation phase. It's critical during the test that the soil be 100% saturated, and the details of getting a specimen to 100% saturation are an important part of the testing. However, for purposes of our discussion, we'll simply assume that the specimen is at 100% saturation before consolidation. There are several different types of triaxial tests. The different tests are distinguished by the drainage conditions applied during the consolidation and shear phases of the test. In phase 1, pressure is added to the water surrounding the specimen, providing a confining and consolidation stress. During the consolidation, the drainage valve may either be open, allowing drainage, or closed, creating an undrained condition. If the valve is closed, we call the test unconsolidated and use the letter U to label this phase. Since the specimen is saturated at the start of the consolidation phase, there can be no change in the volume of the specimen when the valve is closed, and excess pore pressures will be generated during this phase. If the valve is open, the specimen is free to drain, and we call this phase consolidated and use the letter C to label it. In this case, the soil will be allowed to change volume, and all excess pore pressures will be dissipated by the end of the consolidation phase. During phase 2, the shear phase, again, the drainage valve may either be open or closed. If the valve is open, we call the phase drained and use the letter D as a label. In a drain test, the assumption is that there are no excess pore pressures generated during shearing. To ensure this is the case, we must run the test very slowly so that any pore pressures that might be generated during shearing have time to dissipate. This is particularly important for clay soils, which have a low hydraulic conductivity. If we close the drainage valve during the shear phase, we have an undrained test represented by the symbol U. There will be no volume change in the specimen in this case, and consequently shear-induced pore pressures will be generated. We commonly measure the pore pressures generated during shear. This allows us to compute the effective stress within the specimen. We use a two-letter designation to identify the different types of triaxial tests. The first letter specifies the drainage conditions during the consolidation phase, and the second letter specifies the drainage conditions during the shear phase. The UU test is an unconsolidated undrained test. In this test, the drainage valve is always closed. This is a total stress test and does not usually entail measuring the pore pressures. It's also called a Q or quick test since we do not have to wait for consolidation, nor do we have to wait for drainage during the shear phase. The CD test is a consolidated drain test. In this test, the drainage valve is always open. This is an effective stress test since no excess pore pressures are allowed to accumulate. It's also called an S or slow test since we have to wait for consolidation to be completed during phase 1, and we have to shear the specimen slowly during phase 2 so that no excess pore pressures are generated. The CU test is a consolidated undrained test. In this test, the drainage valve is open during consolidation but closed during shear. It's also called an R test. presumably because it's faster than an S test but slower than a Q test. During shear, we normally measure the pore pressures generated. This allows us to compute both the total and effective stresses during shear. Finally, we sometimes perform an unconfined compression test on cohesive soils. Strictly speaking, this test is not a triaxial test. It's not performed in a triaxial cell. It's a simple compression test without any consolidation or any confining pressure. It's similar to an unconfined compression test on a concrete cylinder. Since the test is not performed in a triaxial cell, we have no control over the drainage conditions. In this test, we shear the soil very quickly and assume that there's no drainage. This test is equivalent to a UU test with sigma 3 equal to 0. In the next part of this webcast, we will examine the stress paths followed in each of the 4 tests we just discussed. In each case, we'll present a schematic of the specimen on the left side showing the boundary conditions and the applied stress. On the right, we'll draw the Mohr circles for the tests, plot the failure envelope, and determine the strength parameters phi and c. In the unconfined compression test, a vertical stress is applied to the soil without any lateral confining stress. That is, the minor principal stress, sigma 3, is equal to 0. Therefore, the Mohr circle for this test are all tangent to the tau axis. The vertical stress is then increased until the soil fails. At failure, the maximum principal stress is denoted sigma 1f, or simply called sigma 1 at failure. This is a total stress test. We have no measure of the pore pressures, and we cannot determine the effective stresses in the soil. The peak shear stress at failure is a measure of the undrained strength, SU. There is no failure envelope for the unconfined compression test since we have only one more circle in this test. The UU test is another total stress test. Like the unconfined compression test, we do not measure pore pressures and do not compute effective stresses. The purpose of the UU test is to determine the undrained shear strength, SU. The drainage valve is closed throughout the UU test. Initially, there is no stress on the specimen, and the Mohr circle appears as a point at the origin of the Mohr-Coulomb diagram. As we apply the cell pressure during the consolidation phase, the Mohr circle remains a point because sigma 1 and sigma 3 are both equal to the cell pressure. However, the Mohr circle moves to the right along the sigma axis as the cell pressure increases. Once the consolidation phase is complete, the shear phase starts by increasing the vertical stress applied to the specimen. The minor principal stress, sigma 3, does not change as we shear the specimen. We continue to increase the vertical stress until the specimen fails. Again, the maximum principal stress at failure is sigma 1f, and the soil has an undrained strength, SU. Because the drainage valve was closed during the consolidation phase, no consolidation occurred, and the soil did not gain any strength during this phase. Therefore, the undrained strength under confining stress is no greater than the undrained strength measured by an unconfined compression test of the same soil as shown here. Similarly, if we conduct another test on an identical specimen, but raise sigma 3 during the consolidation to the point shown, the soil still would not gain any strength because no consolidation is allowed. This third test would also have the same undrained strength as the 2 previous tests. If we plot the total stress failure envelope for the test, it will have 0 slope and intersect the tau axis at SU. This is known as the phi equals 0 condition. Saturated clays loaded in undrained conditions fail under phi equals 0 conditions. Now let's consider the consolidated drained or CD test. In this test, the drainage valve remains open during both the consolidation and shear phases, and any excess pore pressures that might be generated are allowed to dissipate, so there's no excess pore pressure. Therefore, the effective stress and the total stress are equal. This is an effective stress test. During consolidation, the Mohr circle again moves from a point at the origin to a point at the consolidation stress, sigma 3. But in this case, sigma 3 is an effective consolidation stress because there are no pore pressures and the soil will consolidate and increase in strength. Sigma 1 is then increased until the soil fails. But in this test, the shearing is done so slowly that no pore pressures are generated. Therefore, the major principal stress at failure is also an effective stress. If we test a second specimen, but consolidate it to a higher confining stress, the soil will gain strength during the consolidation process. When it is sheared, it will have a larger, more circle at failure as shown. Likewise, if we run a third test at yet a higher confining stress, again, the soil will consolidate and have an even larger, more circle at failure. Using the three failure circles shown, we can plot the failure envelope as the line tangent to the circles and compute the friction angle phi prime and cohesion C prime. In this case, this will be an effective stress failure envelope, and phi and C will be effective stress parameters as noted by the use of the prime symbol. Let's look at our final test, the CU test, or Consolidated Undrained test. In this test, the drainage valve is open while the confining stress is applied and remains open until the soil is consolidated and all pore pressures are dissipated. The drainage valve is then closed, creating an undrained condition for the shear phase of the test, and we will be measuring any excess pore pressures that are generated during shear. The vertical stress is then increased until the soil fails. Since we are measuring pore pressures during the test, we know the change in pore pressure at failure, delta U. Knowing both the total stresses and the pore pressure at failure, we can compute the effective stresses at failure and plot the effective stress more circle shown here with dashed lines. This circle is offset from the total stress circle by a value of delta U. In this case, we have a negative excess pore pressure, so the effective stress is greater than the total stress, shifting the Moore circle to the right. As in previous tests, we can test a second specimen at a higher consolidation stress. We can then shear this specimen until it fails and determine the total stress circle at failure for the specimen. Again, we'll know the pore pressures at failure, so we can also plot the effective stress circle at failure, here shown with dashed lines. Finally, we can test a third specimen at a higher confining stress, and we will obtain another set of total and effective stress circles at failure. We now have two sets of failure circles. The solid circles represent total stresses at failure, and the dashed circles represent the effective stresses at failure. If we consider just the effective stress circles, we can plot the effective stress failure envelope and determine the strength parameters phi prime and C prime. Therefore, from a CU test with pore pressure measurements, we can determine the effective stress strength parameters, even though the shear phase is in an undrained condition. So now that we've covered the basic triaxial tests, let's discuss some of the advantages this test has over the direct shear test. The triaxial testing procedure gives us control over drainage conditions, both during consolidation and shear. Therefore, it allows us to measure either the drained strength or the undrained strength of a soil. The shear plane is not confined to a fixed plane as it is in the direct shear test. This gives us a more realistic failure surface and a better measure of the strength of a soil. The boundary conditions are controlled and known. This allows us to plot complete Moore circles and determine the stresses on the failure plane. Finally, we can measure both axial and volumetric strains during the test, which allows us to measure the stress-strain properties of the soil. So let's summarize. The triaxial test has the following characteristics. The test is relatively difficult and time-consuming to run, with the exception of the UU test, which can be run very quickly. However, both the CD and CU tests must be run very slowly so that shear-induced pore pressures can dissipate or equilibrate throughout the specimen. The data is more difficult to analyze than the direct shear data, but at the same time, we get much better information from these tests. Finally, the strength parameters measured in the triaxial test are more accurate than those measured in the direct shear test. You should now review the learning objectives for this presentation. If you don't feel you've achieved these objectives, now would be a good time to review the presentation. Example 1210 in your text presents data from a CU test. You should review this example before class.
The Eso es todo, amigos.
Hello, this is Professor Kitch, and welcome to.
You followed, okay, and now put little effort and try to understand the test, and you can read for your exams, okay. So with that we'll stop today.